Hello students and welcome back to my Hanson Math YouTube channel. Today's lesson regards finding the derivative. In this video, we will recap the previous lesson, discovering the derivative, which you can also find on my YouTube channel. Specifically, we will work on finding the derivative of quadratic, linear, square root, and rational functions. And I will tell you just right ahead of time that the worksheet that I'll be working off of, as well as the answer key, are available on hansonmath.com. The links are located right in the description, right underneath the YouTube video. The definition of the derivative is essentially just the slope, which f of x plus delta x minus f of x is this vertical change or rise, and delta x is just a horizontal change or run. Okay, so the derivative is finding the slope, which can be seen by using the tangent line to a point along a curve. So the derivative is the slope of the tangent line, and it's the instantaneous rate of change. That means a change at that very instant. It's not an average change, but a change at a specific instant in time. So the first thing to note here is the definition of the derivative, f prime of x. The little prime means the derivative is the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. So we're going to use this for all of the example problems today. Specifically on this one called We All Try number 1, we're going to find the derivative of f of x equals 5x squared minus 3x plus 4 using this formula. After that, we're going to evaluate the rate of change exactly at the point 1 comma 6. And then after that, we will write the equation of the line tangent to 1 comma 6, and we'll confirm with Desmos. So you'll see for the 4 examples we're going to do today, I use the same kind of script each time, where I write out a little bit of a template, which makes it easier for students to fill in. I found, as I had a tremendous difficulty with this when I was in high school, first learning calculus. So if you break down the definition of the derivative a little bit, you'll note that this first chunk here is plugging into the function x plus delta x. So I have that here, where we're going to plug in x plus delta x everywhere that you have x. So we had x here after the 5 and after the 3. So we're going to plug in x plus delta x here and here in just a moment, okay? So the function ends with plus 4, which is right here. Then we up here we have minus f of x. That's like the second chunk to me. So minus f of x just means you subtract the function, as you'll see. And the third chunk is dividing by delta x, which is right here, which is consistent from problem to problem. Okay, so working from left to right, we have 5. I'm going to plug in x plus delta x, okay, and that's squared because this was x squared, minus 3x. Instead of 3x, we're going to replace x with x plus delta x. And then the constant of our function was plus 4, which goes here. Okay, that's what I call the first chunk, which is the f of x plus delta x chunk. The second chunk is minus f of x, which you'll see here. F of x is just a function, so we're going to subtract the function, which is 5x squared minus 3x plus 4, and it's all divided by delta x, okay? So that is the setup. So at this point, we're ready for a rewrite. We have f prime of x, which is the derivative, equals the limit as delta x approaches 0. And now we have to multiply it out. So we have our 5. And then we're multiplying by x plus delta x squared. So that's squaring a binomial. So you could write it out twice, x plus delta x plus delta x. You could FOIL it, that works fine. Or you can remember the shortcut when you're squaring a binomial. You square the first, so that's x squared. And then you multiply 2 times the first times the second, so that's 2 times x times delta x, and then you square the second term. So delta x squared is just that, delta x squared, close the parentheses, this minus 3, which is like distributing a negative 3. So I've got negative 3 times x is negative 3x. I've got negative 3 times delta x, which is a negative 3 delta x, and the parenthesis closed. Okay, now I'm at my plus 4. I copy that down, plus 4. Okay, that's kind of like what I call chunk 1, where you evaluate f of x plus delta x. Now we're just subtracting the function, so it's like distributing this negative. It's like distributing a negative 1. So we have negative 5x squared, negative 5x squared. A negative times a negative is positive, so it's positive 3x. And a negative 1 times 4 is negative 4. Okay, all of that all over delta x. Okay? The next step here is going to be to distribute this 5. So I'm going to rewrite again. We have the derivative f prime of x is equal to the limit as delta x approaches 0 of, now we're going to distribute this 5. So we got 5 times x squared would be 5x squared. 5 times 2 would be 10, and that's x delta x. And then we also have, so that was there, and then the 5 also multiplies to the delta x squared, so that would be 5 delta x squared. We have minus 3x minus 3 delta x plus 4, I'm just recopying the numerator, minus 5x squared plus 3x minus 4, all over delta x. Okay, well, what's next? At this point, we're going to combine like terms, and you're going to notice that a lot of things cancel out. So if we start by looking at this 5x squared, if you inspect all the way down yonder, you're going to see a negative 5x squared. So those terms cancel. Boom, boom, because we have opposite signs. You'll also notice that right here we have a negative 3x, and down further we have a positive 3x. So those terms offset or cancel out. Boom, boom. You'll also notice that here we have a plus 4, and at the very end we have a minus 4. Those two will cancel out. So this is going to be a common theme with finding the derivative. Lots of things cancel out if you do it correct. So now what is left? We are left with 10x delta x plus 5 delta x squared and minus 3 delta x. Those are all different terms because x delta x is not the same as just delta x, and it's not the same as delta x squared. So it's time for a rewrite. Let's do f prime of x is equal to the limit as delta x approaches 0. But before we do our rewrite, notice, what do all of these terms have? They have delta x, and delta x. Since they all contain a delta x, I'm going to factor out a delta x. So I'm going to factor out delta x out of the numerator. And if I factor it out, like if I start here, if I pulled out the delta x, I have to just multiply that by 10x. So I've got 10x. I pulled out a delta x. So for this term here, I need the 5. And since I pulled out a delta x, I don't have delta x squared anymore. I just have delta x. And then minus, I'm on this final term here, minus a 3. And the delta x was already included there. Okay? So that's all over delta x. Okay? Now, you'll notice since we factored out a delta x, since it's factored out, you'll notice that the delta x in the numerator divides out with the delta x in the denominator. So now, if I evaluate delta x is equal to 0, I won't get division by 0. So now I can actually evaluate the limit. So at this stage, what I'm going to do is the following. I'm going to do a rewrite and say that I have f prime of x is equal to the limit as delta x approaches 0, and I have 10x plus 5 delta x minus 3. So at this point, I'm going to substitute in delta x equals 0. So what I'm going to do is evaluate the limit, because now I won't get division by 0 because of this denominator, because we just got it to cancel out. Now, keep in mind that we're not replacing x with 0, we're replacing delta x with 0, which is very important. So now we have 10x plus 5 times, instead of delta x, we're going to replace delta x with 0, and then minus 3. So if you evaluate this, what do we have? We have 10x, 5 times 0 is 0, and then we have our minus 3. So that is it, my friends. That is the derivative f prime of x. So the derivative for this problem is 10x minus 3. We found it. So what this new function f prime of x will do is it will give us the slope of the tangent line to any point we want to investigate on the curve. So now that we have our derivative being 10x minus 3, we can find the rate of change, or the slope, at the point 1 comma 6. So what I want is I want the slope, which we'll call m. I want the slope m at the point 1 comma 6. So what I'm going to do is I'm going to take the x value here, which is 1, and I'm going to substitute it into the derivative. So f prime, the derivative evaluated at 1 from the x coordinate, is equal to, instead of 10x, it's 10 times 1 minus 3, right? So we're using 10x minus 3, but x is worth 1. So now we have 10 times 1 is 10, minus the 3 is 7. So 7 is the slope at the point 1 comma 6, okay? So now we have the derivative. To find the slope at any point is 10x minus 3. The slope at a particular point on the curve, at point 1 comma 6, the slope is 7. So that was this was part A, this was part B. So now we will find part C, which is the equation for the tangent line to this point 1 comma 6. So to do that, we will do the point slope form for a linear equation. Y minus y1 equals the slope times x minus x1, and we'll plug in. So we have y minus, the y coordinate is 6, equals the slope is 7, times x minus the x coordinate, which was 1. Okay, so now we have y minus 6 equals, distribute, 7 times x is 7x, distribute again, 7 times minus 1 is minus 7. Finally, get y by itself, add 6 to both sides. So we have y equals 7x minus 1. Okay, so keeping in mind that our original function, the original function f of x, was a parabola. It was 5x squared minus 3x plus 4. Its derivative, f prime of x, is this, 10x minus 3. The slope at the particular point 1 comma 6 is a rise over run of 7, or 7 over 1. And the equation of the line tangent to the point 1 comma 6 is y equals 7x minus 1. So the last thing we're going to do here is we're going to vet this out on Desmos and make sure indeed that this line here is the tangent line to the original function at the point 1 comma 6. So let's go over to Desmos and check it out. All right, so over here on Desmos, you see our original function, f of x equals 5x squared minus 3x plus 4. It's this nice red parabola. We were looking for the tangent line to the point 1 comma 6. 7x minus 1 is the tangent line. Bam, and there you can see it right there. It just barely touches this point 1 comma 6. Okay. Now, if you saw something crazy, like the line was cutting through the parabola, you'd know you made a mistake. but this vets our solution. Okay, at this point, I'd like you to try, y'all try number 2. Find the derivative of f of x equals 4x squared plus 6x. I've given you the template provided here to help get you started. So you're going to find the derivative f prime of x. Once that's done, part B is to evaluate the rate of change at the point -2, 4. So you'll have to plug in the -2 into f prime of x. And then part C is write the equation to the line tangent to -2, 4, which you do with the point slope formula as I chronicled in We Try number 1. So at this time, I'd recommend that you hit pause and try y'all try number 2. When you're finished, press play and we'll go on to We Try number 3. Okay, moving on to We All Try number 3. At the top of the screen again, we have the definition of the derivative. This time we're going to find part A, we're going to find the derivative to f of x equals 7x minus 2, which is a linear equation. Part B is to evaluate the rate of change at -1, -9, and then part C is write the equation of the tangent line. Okay, so let's do it. So again, thinking about it in terms of chunks, the first chunk is to take the function, which is 7x minus 2, and here you have 7x minus 2, but the x has been replaced with an open parenthesis because we're going to replace it with x plus delta x, okay? We're going to plug in x plus delta x, that's step 1. And then the -2 was just the constant of the function. Now, the second part of the numerator when you're taking the derivative is to subtract the function itself. So you're subtracting the function, which is 7x minus 2. So 7x minus 2 goes into this end parenthesis here, which is f of x. And as standard for the derivative, you're dividing by delta x, all right? So once you have it all plugged in here, we can do a rewrite, and we can say f prime of x is equal to the limit as delta x approaches 0. And we can simplify, we can, distribute, FOIL, whatever the case might be. In this case, we have a 7 in front of the parentheses, so we have to distribute. So we have 7 times x is 7x, plus 7 times delta x is 7 delta x, the parenthesis closed, so I stop distributing. I also have the -2, so I'm going to copy that down, -2. And then keep in mind this minus the parentheses here, it's like a -1 distributing, boom, boom. So -1 times 7x is a -7x, and a -1 times a -2 is a +2. Okay, so we did all the arithmetic we could in the numerator, so we're going to put everything over the denominator, which is delta x. Okay, so at this point, what we're going to do is a rewrite. F prime of x is equal to the limit as delta x approaches 0. And before we do any kind of a rewrite, we want to see what cancels and if we can combine anything. And again, like I said, with these derivatives, a lot of things cancel. So we have 7x, and if you inspect down yonder, we have a -7x. Those cancel. Boom, boom. We have a -2, and at the tail end, a +2. Those offset or cancel. Boom, boom. We're left with 7 delta x over delta x. Okay? So now if we do a rewrite, we have f prime of x is equal to the limit as delta x approaches 0. And notice that delta x divided by delta x, those cancel, okay, becomes 1. So you have 1 times 7, which is just 7. So the derivative here, we have no variable. The derivative is 7. So 7 is f prime of x, okay? We're done. The delta x is canceled out. There's nothing to plug 0 in for delta x because the delta x's went away. So for this one, the derivative is 7. And since there is no variable, there's no x left, this is telling this lets you know that this function has the derivative is 7. It means that it has a constant rate of change everywhere. Constant rate of change everywhere. And specifically, it's 7. Okay? So that means the rise over the run, the change, at any point on the function, the rate of change is 7. And that makes sense because if you plug this into a graphing calculator, 7x minus 2 is a linear function. So there's no point in doing part B to evaluate the rate of change. The rate of change at every point on this function is 7 since it was linear to begin with. So there really is no the tangent line and the function is the same. So again, this is as far as you need to take these. It's just 7, okay? So if you have a linear equation to begin with, something's going to happen like this in all of your derivative problems where you just end up with a constant number. Hopefully that last example made sense. If so, it's time for y'all try number 4. So I want you to find the derivative of f of x equals negative 2x plus 1. Remember, this is a linear function to begin with. And I have the little script for you, so it's ready to go for you to start plugging in the x plus delta x and the function. So again, good luck. If you need to look at we try number 3, you may. So hack away at y'all try number 4, and when you feel you're finished, resume the video and we will move on to we all try number 5. This time around, we're going to find the derivative of a square root function, specifically part A, find the derivative of f of x equals the square root of x minus 4. So we have the square root function. After that, we're going to evaluate the instantaneous rate of change at the point 5, 1, and then we'll write the tangent line to that point and confirm with Desmos. So what I've done is I've set up my little template here, and let me get out my pen. So again, this is our function, square root of x minus 4. So I have it written in the numerator, square root of x minus 4, but instead of x, I left it blank because our first move is to plug in x plus delta x. That's what I consider the first chunk of the numerator. The second chunk is always subtracting the function. So we're going to subtract the square root of x minus 4. So subtract the square root of x minus 4. And then the denominator is just delta x. So there is your original substitution. So note, we can't plug in 0 for delta x right off the gate, because if we did, we'd have division by 0. In fact, if we plugged in a 0 for delta x in the numerator, we'd have the square root of x minus 4 minus the square root of x minus 4, so we'd get 0 over 0. So this goes back to the lesson we did previously on limits, where if you have two terms with a square root, your best bet is to multiply by the conjugate. So that is the strategy we are going to take in this one as we move forward. So let's do it. So we have a rewrite. Oh, gotta get my pen. We've got f prime of x, the derivative, is equal to the limit as delta x approaches 0. All right, so we're going to do a rewrite. I've got the square root, and under the square root for this first chunk, I've got x plus delta x minus 4. That was all under this square root. Then I have a subtraction operation and another square root. That was the square root of x minus 4. And I have all that over delta x. Now, again, when we looked at the limits chapter, we talked about when we had something like this, your best bet is to multiply by the conjugate of the numerator. So if you look at the numerator, we have the square root of x plus delta x minus 4. and we're subtracting the square root of x minus 4, the conjugate would be the same thing, but instead of a subtract between these two square roots, we're going to do addition. That would be the conjugate. So we're going to multiply by the square root of x plus delta x minus 4. That was just this term right here. But instead of minus, we're going to do plus the square root of this term, which is x minus 4. Okay? And whatever we do to the numerator, we have to do it to the denominator, because if not, we're changing the value of the function. So by doing this, we will basically be multiplying by 1 whole. Multiplying by 1 whole, of course, does not change the value of anything. Okay? So that's the deal. This is called multiplying by the conjugate. So the only thing I'll add to this is I'm going to put the numerator in parentheses. I'm going to put the conjugate stuff in parentheses. The f prime of x is equal to the limit as delta x approaches 0. When you're multiplying something by its conjugate, essentially you're doing FOIL, first, outer, inner, last. But notice that since we have the same terms here, and the only difference is minus and plus, the outer and the inners will offset or cancel out. So we really only have to multiply the first times the first and the last times the last. So what I'm talking about is this, and let me see if I can clear this up a little bit. And so what I'm talking about is the following. We're going to multiply this term right here by this term. That's what I mean by first times first. So the square root of x plus delta x minus 4 times itself, the square root of x plus delta x minus 4, you get just that term without the square root symbol. The square root cancels out. So we're left with x plus delta x minus 4. Okay, you guys have seen this before. It's like the square root of x times the square root of x is just x, or the square root of 9 times the square root of 9 is just 9. So you have the square root of this term times itself is just the items here without the square root symbol, right? Hopefully that's not a big surprise. As we just talked through, the outer and the inner products will cancel out due to the minus and the plus. So now we just have to multiply the last, which would be a negative root x minus 4 times a positive root x minus 4, which will be a minus. The square roots will cancel out, so you'll just have x minus 4. Okay, so that is your new numerator. Your denominator is delta x, but it's delta x times this part of the conjugate, which was the square root of x plus delta x minus 4, x plus delta x minus 4, plus the square root of this piece here, which is the square root of x minus 4. Okay? So what we'll do next here is we will do another rewrite. So we have f prime of x is equal to the limit as delta x approaches 0. And we have, in the numerator, we have x plus delta x minus 4. And then note that this minus in front of the parentheses, it's like a minus 1. So it's like distributing a negative 1 to the contents inside the parentheses. So specifically, that's negative 1 times x would be a minus x. And a negative 1 times a negative 4 is a positive 4. And that's all over this big denominator of delta x times the square root of x plus delta x minus 4 plus another square root of x minus 4. Okay, I hope you can follow my sloppy writing. At this point, I'm going to move up my screen and we'll finish off this derivative. All right, so let's do a rewrite and clean up the numerator. So we have f prime of x is equal to the limit as delta x approaches 0. And notice if we inspect the numerator, we have some things that will drop out here. We have an x as the first term in the numerator. If you look down yonder, you see a minus x, so those will offset or cancel out. You'll also notice that you have a minus 4 and a plus 4, and those terms too shall cancel out. So in the numerator, you're not left with much. You're left with one term, which is just this delta x right here. So in our rewrite, we'll say we have the limit as delta x approaches 0 of delta x over the denominator, which is delta x times a bunch of stuff. The square root of x plus delta x minus 4 plus the square root of x minus 4. Now, what do you notice happens at this point? You have a delta x in the numerator and you have a factored out delta x in the denominator. So lo and behold, lucky for us, those cancel out. Boom, boom. And of course, when we say cancel out, we mean that they divide to one whole. So you're left with 1 on the numerator. It's not like you have nothing, okay? So delta x divided by itself is 1, which is what you have in the numerator. So when we do our final rewrite here, we have f prime of x is equal to the limit as delta x approaches 0 of 1 over the square root of x plus delta x minus 4, that was the first square root, plus the second square root, which is x minus 4. So at this point, ladies and gentlemen, we can evaluate this limit as delta x approaches 0 via direct substitution. So we can plug in the 0 for delta x. So we have 1 over the square root of x plus delta x now is 0 minus 4, that was the first square root, plus the second square root is x minus 4. Just keeping in mind that we're replacing delta x with 0, not regular x. So now, what do we have? We have 1 over, we have the square root of x plus 0 minus 4. The 0 doesn't do anything, so we have x minus 4 plus another square root of x minus 4. So we have 1 over, we have two terms of x minus square root of x minus 4. So what is the square root of x minus 4 plus another square root of x minus 4? Well, it's two of those. It's two groups of the square root of x minus 4. That is your derivative of this function, which is f prime of x right here. Yeehaw. So f prime of x, the derivative is 1 over 2 times the square root of x minus 4. So if we've come that far, that's part A, that's the derivative in general. Now, if we substitute in any x value whatsoever, it will give us the rate of change or the slope at that point. So part B says, evaluate the rate of change at the point 5, 1. So we want the slope, m, at the point 5, 1. All right, so let's take our derivative, f prime, and we'll evaluate it at an x value of 5. So f prime of 5 is equal to 1 over 2 times the square root of, instead of x minus 4, we plug in the 5. So it's 5 minus 4. So that's to say we have 1 over 2 times the square root of 5 minus 4 is 1. So that's to say we have 1 over 2 times the square root of 1, which is just 1 over 2. So our slope here is 1/2 at this particular point, 5, 1. Okay, so the rate of change is 1/2. So that brings us to part C. Part C is finding the tangent line. So we have y minus the y coordinate, which is 1, equals the slope, which is 1/2, times x minus the x coordinate, which is 5. Okay, that's our point slope form. To get it into y equals mx plus b, we will distribute that 1/2. So that is 1/2 x minus half times 5 is 5/2. Okay, last step here is to add this 1 to both sides. So we'd have plus 1 plus 1. So in the final analysis, we have, boy, that's a terrible arrow. We have y equals 1/2 x. Now we have to figure out what is negative 5/2 plus 1. So that's negative 5/2 plus 2/2, which is a negative 3/2. That is the line that's tangent to f of x at 5, 1. Okay? So now we found everything. We found the derivative for this function is 1/2 times the square root of x minus 4. We found that the slope at the point 5, 1 is 1/2. And we found that the tangent line's equation is y equals 1/2 x minus 3/2. So with this in mind, you can reflect on it, rewind if you need to. I'm going to go on to Desmos, graph f of x, and graph the tangent line, and make sure it all adds up. The shortcut for square root is just to type SQRT. SQRT, see it pops up the square root, and it was x minus 4. That was our function, as you can see right here. And the tangent line was y equals 1/2 x, 1/2 x plus 3/2, minus 3/2. That's why it doesn't look right. And there you can see, boom, there is the point of tangency right there, 5, 1, which is what we desired. That's the equation of the line tangent to the point 5, 1 on the square root of x minus 4. So again, the derivative finds you the slope of the tangent line or the rate of change at a particular point. So now that we've completed we all try number 5, it's your turn. Y'all try number 6. So I want you to find the derivative of f of x equals the square root of x plus 8. Okay, here is your template here. Once you've done that, part B is to plug in into the derivative, f prime, plug in 1 for x, so that will be the slope or the rate of change at that point, and then use the point slope form to write the tangent line equation at 1, 3. Okay, again, this is very, very similar to we all try number 5, so hit pause, try to knock out y'all try number 6, and when you're done with number 6, we'll move on to our last example together. We all try number 7. So here it is. This is the last example together. We all try number 7. This time we're going to do a rational function. We have part A, find the derivative to f of x equals 1/x plus 2. So we're going to work on that first, and then we're going to evaluate the exact rate of change at the point 0, 1/2, and then find the tangent line to that point. So you'll notice once again, I have my template set up, and this one's a little bit irritating because we have fractions in the numerator, so it's kind of like a fraction over a fraction, so to speak. That's going to be instructive regarding what to do moving forward. But first, let me break this down for you guys a little bit. Notice that this first chunk is f of x plus delta x. So I write out my equation, which is 1/x plus 2. And instead of the x, you're going to plug in x plus delta x per usual, okay? The second chunk is just subtracting the function. So you're subtracting the function, which is 1/x plus 2, and it's all over delta x. So this is the setup. Now, at this point, you might wonder what would happen if you plugged in direct substitution delta x equals 0. If you did that, you'd have division by 0. You'd actually have 0/0 if you want to try to plug in 0 for delta x. So when you have 0/0, You have to try different techniques. The last problem was using the conjugate. This one is going to be common denominators for the fractions. So we're going to work on getting common denominators. But before we do that, my first step here, since this fraction within a fraction thing is going to cause us a problem, I'm going to get rid of dividing by delta x, and I'm going to change it to multiplying by 1 over delta x. So you guys should be familiar with this. Dividing is the same as multiplying by the reciprocal. So instead of dividing by delta x, we're going to multiply by 1 over delta x. That's going to make things easier the further we get, so that we don't have to look at stacked fractions. That just gets kind of messy and annoying. All right. So at this point, let's do a rewrite. We've got f prime of x is equal to the limit as delta x approaches 0. And what we're going to do is we're going to attempt to build common denominators. So let's first rewrite the first fraction, which is 1 over x plus, I'm right here, x plus delta x, and then plus 2, okay? And then I'm going to space this out a little bit. I'm going to leave a little bit of room. Then I'm going to bring down my minus right here. And then I'm going to put my next fraction, which is from here, 1 over x plus 2, 1 over x plus 2. And then I'm going to leave some room. And then I'm going to put my multiply by the 1 over delta x, which was from here, okay? So what I'm going to do is I'm going to put these trinomial and binomial in parentheses, and now we're going to think, what would we have to do to get common denominators? Well, since these denominators are completely different, to have common denominators, you kind of have to like make a swap. So the common denominator would be this trinomial times this binomial. So you've got the trinomial here, so you need the binomial. So we're going to have to multiply this fraction by x plus 2 over itself, x plus 2, which is like multiplying by 1. That's why you're able to do that. And then in the second fraction, we have the x plus 2, but we don't have that trinomial. So you have to multiply by that trinomial, which is x plus delta x plus 2 to the top and to the bottom. So again, it's like you're multiplying by 1. It doesn't change the value. And then we, at the end here, we're multiplying by 1 over delta x, okay? So what this will give us is the following as we do our rewrite. We have f prime of x is equal to the limit as delta x approaches 0. And I'm going to put everything over the common denominator. So the common denominator is the trinomial piece, which is x plus delta x plus 2, times the binomial piece, which is x plus 2. That's our common denominator. Now I'm going to put the numerator information up top. So here we have a 1 times x plus 2. 1 times x plus 2 is just x plus 2. And then here I have, this is like -1, and it's multiplying, distributing to boom, boom, boom. So I've got -1 times x is negative x. I've got -1 times delta x, which is negative delta x. And I've got -1 times positive 2, which is -2. All right. So this step allowed me to have common denominators. I combine the numerators, like hopefully you guys could follow what I did. Now I just have to, instead of dividing by delta x, I'm multiplying by 1 over delta x for the sole purpose to try to avoid a fraction within a fraction, okay? So at this point, I'm gonna clear up my screen and we'll finish off this derivative. So we're gonna continue on here with the rewrite. We have f prime of x is equal to the limit as delta x approaches 0. And now let's clean up our numerator, combine like terms. Let's see if anything cancels, which is our hope. My first term here is an x. Down yonder, I see I have a minus x, so those will cancel. Boom, boom. I have a positive 2, and I have a minus 2. Those cancel to 0. Boom, boom. So, ladies and gentlemen, what am I left with in the numerator? I'm left with nothing more than the negative delta x. So I have negative delta x over, I'm going to recopy my denominator, which is the trinomial x plus delta x plus 2 times the binomial x plus 2 times this 1 over delta x, which again was my division by delta x from the beginning. Now, let's do a rewrite and let's see what happens. We have f prime of x equals the limit as delta x approaches 0. Now, what do you notice here? We have a delta x at the top in this numerator of this fraction multiplied by a delta x in the denominator of the other fraction. Those will cancel. So cancel, cancel. So now if we do our rewrite, we have a negative times 1, which is negative 1, over this trinomial binomial product, which is x plus delta x plus 2 times x plus 2. Okay? At this point, we've simplified it as far as we can go. So now let's try to substitute in the limit as delta x goes to 0. So let's try direct substitution and let's see what happens. So we have negative 1 over x plus delta x goes to 0 plus 2 times x plus 2. Okay? So now if we do a rewrite, we have negative 1 over x plus 2, okay, right? Because 0 plus 2 is still 2, times the other x plus 2. Well, what's a more succinct way we can write that? We can write negative 1 over x plus 2 quantity squared. That is the derivative, f prime of x, for this problem. Done. It's negative 1 over x plus 2 squared. Okay? That is the derivative now, which will find us the rate of change or the slope at any point on this original function. So what I'm going to do next is slide this up a little bit and we'll knock out the slope or the rate of change at a particular point. Part B asked us to find the slope at the particular point 0, 1/2. The slope at 0, 1/2, okay, where this is our x and this is our y coordinate. So to do that, to find the slope, we plug into the derivative. So the derivative was, or is, f prime of x, but we're going to plug in 0 for x, is equal to, we have a negative 1 in the numerator, over, in the denominator, we have x plus 2 squared, but that's going to be 0 plus 2 squared. So that's to say we have a negative 1 over 0 plus 2 is still 2, so that's 2 squared. So we have a negative 1 over 2 squared is 4. So that is our m, or our slope, at the particular point of 0, 1/2. So it's important to note that's not the slope everywhere because the function's changing. That's just the slope at the particular point, 0, 1/2. Okay, so that finally will lead us to part C. Part C is to write the linear equation of the line tangent at that point. So we have our point slope form, which is y minus the y coordinate, which is 1/2. And that has to equal the particular slope, which we just found was negative 1/4. So that's negative 1/4 times x minus the x coordinate, which was 0. So now we have y minus 1/2 equals, distribute, negative 1/4 times x is negative 1/4 x, and negative 1/4 times 0 is nothing, so I'm not going to worry about that. So last step here is we're going to add 1/2 to both sides. We end up with y equals negative 1/4 x plus 1/2. So that should be, if everything went well, that should be the tangent line at the point 0, 1/2 of the original f of x equation, which was 1 over x plus 2. So now we'll pop over to Desmos, we'll graph 1 over x plus 2, we'll graph this tangent line, and we'll make sure that its tangent or just barely clips this point, 0, 1/2. Let's take a look. So over here on Desmos, you see f of x equals 1 over x plus 2. That was our rational function with these two branches. Now if I pop in the tangent line, which is y equals negative 1/4 x plus 1/2, bam, there it is in blue, and you can see its tangent or only crosses the point 0, 0.5, which was our 0, 1/2, which is exactly what we wanted. So we got the tangent line right, we got the derivative right, we got everything right. So we are made in the shade. Everything went perfect. All right, ladies and gentlemen, once again, we've reached the end of the line. This is the final problem. This is y'all try number 8. So very similar to number 7, you're going to find the derivative of f of x equals 1 over x minus 5. I've given you my handy dandy little patented template right here. Part A, you're going to find the derivative, f prime of x. Part B, you're going to find the slope at the particular point, 6, 1, where you plug in 6 for x. And then you find the equation of the tangent line using point slope. I hope this is coming together for you all. If this is your first time doing these derivative problems, it should be challenging, no doubt. It takes months and years to learn calculus, so Rome wasn't built in a day, and neither is calculus. You just have to be patient. So once again, I thank you for watching this video, and I hope everybody has a wonderful day.